Assalamu alaikum rahmatullahi wa barakatuh. Dear students, this is Dr. Ali El-Moursy again, and we are in the lectures for the microprocessor class. This is the lecture for microprocessor class. We are in lecture number 28, part 2. We are in lecture number 28, part 2. This lecture is discussing the last theoretical chapter, or the last set of slides for this course, which is about the memory, the input-output interface or in-out interface for the x86, 8086 and 8087 microprocessors. This is a very brief and a small chapter. We just want to give you some information about the two things. First is the how the input-output is handled for this microprocessor, and we want also to compare between two different methodology or models of how to perform or implement input-output for the microprocessors. Again, here in the slide number 2, we are showing the picture for the processor here, the 8086 and the 8088, and we can see the different pins. Actually, right now, by the end of the semester here, we have learned most of the pins that are shown here. One pin that we do care about today is this pin. Okay, this pin is related to the as it is indicated here or shown here, M/IO bar. Okay, so this will be our focus of today's lecture. So different, there is some difference between the 8088 and the 8086, but we will not go into go into details for those differences. We just very briefly want to discuss mainly the input-output for the 8086. Okay, there is, as we mentioned, there is a difference between the external bus between them. One of them is 8 bits and the other is 16 bits. We for most of our material we are talking about the 8086, which has a bus of the 8088, which is 8 bits, 1 byte, and the 8086 is 2 bytes, 16 bits. So but both of them, as we discussed before, they can access up to a memory of 1 megabyte. Okay, which means we need an 20 bits address for the address bus. Now, what about the IO? IO is a different device that the microprocessor, or input-output is different things that the microprocessor needs to interface with, similar to the memory. So actually the processor is interfacing with two main items. It's interfacing with the memory and it interfaces with the input-output devices. In the memory, we call them memory addresses. Okay, so since we have 1 megabyte of memory, so we need a 20 bits of what we call the address of the memory. For the IO, they use a slightly different terminology. We don't call them addresses, we call them input-output ports. So they give them the name ports because they actually kind of ports that bridge the information from the input and output devices to the microprocessor and vice versa. How many ports for those machines? We have 64 kilobytes. Okay, 64 kilobytes of different input-output ports. So 64,000, okay, 64,000 different addresses or ports are permissible to be accessed through this machine. Definitely this is a very huge number. Okay, it's not utilized in full. However, we wanted to discuss how the machine is talking or interfacing with the input-output devices. This slide is just discussing something that we want to highlight here, which is actually the microprocessor, in order to save his pins, because extra pins on the microprocessor, those, let's go back to the picture here. So extra pins for the microprocessor means a larger chip, means a more complicated hardware. So the machine has a specific number of pins. As you can see the numbering here, the machine has 40 pins. We cannot increase the number of pins for the processor, because increasing the number of pins increase the power consumption, increase the spaces or the distance between the logics. So the increasing the number of pins has a direct effect on the power consumption, has direct effect on the delay of the chip. So we want, with the same amount of pins, with the same number of pins, we need the microprocessor to be able to deal with the different devices or interface with different things. That's why the pins that you can see here, which are labeled by AD, are for both the data and the address. Okay? Not only that, they are used whether the microprocessor is talking to the memory or the I/O. So basically, there is no specific pins dedicated for the microprocessor to talk to the memory and a dedicated pins to talk to the input output. Those pins are shared between the memory and the I/O. So this brings the direct question here that we can ask: how can the output devices or the processor himself to know whether he is now interfacing or talking to memory or I/O? This is simply defined by this particular pin. So this pin defines whether right now the microprocessor is talking to the memory or talking to the I/O. So this is actually what this slide is talking about. So right now we need to identify, or we need to differentiate between two things. Okay, I jumped directly to slide number 8 in order to highlight this concept. So when the processor sets this pin that we just talked about, pin number 28, to the value 1, that means right now the interface between the processor is going to the I/O, not to the memory. Okay, this pin equals to 0 means he is talking to the processor may talk to two external devices, memory, okay, and in this case he have to put in the IO/mem, he have to put the value 0. If he want to talk to the I/O, this pin should has the value 1. That means right now whatever I have on the data or the address bus will be either directed to the memory or directed to the input output. Okay, agree? Now there are two ways for any microprocessor to talk to the input output. We have two methodology. The first methodology is called the isolated input output, and the other is called the memory mapped. The x86 and x88 processors are using this methodology. This methodology indicates that the microprocessor has dedicated instructions, okay, to talk to the input output. So I cannot use the conventional move or load or store when I talk to I/O. I have particular instructions to talk to the input output devices, as we will see shortly, and those instructions are in and out instructions, as we will see shortly in the following slides. Okay, this is the first difference between the isolated I/O and the memory mapped I/O. So isolated I/O indicates that I have separate address space for the input output devices. Similar to the address space that I have for the memory, I have another address space for the input output. And based on what we have learned in this slide, I have memory of 1 megabyte, so I need 20 bits to address the memory. If my I/O is actually have different 64 kilo or 64,000 different ports, that means I need how many? So 2 to the power what will give me those 64 kilobyte. Okay, anybody knows? Okay, yes, we have here, we have 16 bits. So I have 16 bits for the ports of the I/O. Okay, so in order to talk to the I/O, I have to provide 16 bits of a port. We call it port address, not a memory address. Okay, agree? Now let's go and discuss how the machine would deal with that. Okay, so accordingly, for the x86 and 8088 and 8086, we have a separate address space for the input output. Okay, يبقى address space for the memory different from the address space for the memory for the input output ports. That means if I specify an address like this, okay, sorry, this is an address. Okay, how many bits here? I have 16 bits. This address, okay, could be an address for the I/O. Okay, this address, okay, is different from another address in the memory. So if I have this address in the memory, this is pointing, definitely the memory address should be 5 hexadigits. Okay, so those two addresses are different because this is for the input output and this is for the memory. Okay, so the memory and the address, the I/O, have different address spaces, separate address spaces. Okay, type. Now this picture is simply showing if I ever storing the ports into a memory. Okay, so that means if I have here 1 byte width of memory, so the ports here will be stored. Each 16 port will indicate some port number. So port 0 is actually will consumes 2 addresses here or 2 memory locations here. So I can store the port addresses in some memory for me in order to access the different addresses. Okay, the total size of this is definitely goes from 0000 till FFFF. Okay, this is the address space for the isolated input output type. What else we want to discuss here? Okay, since we are talking about isolated I/O, as we mentioned, we have a dedicated instructions to access the memory and to access the input output ports, and those instructions are instruction in to get data from the port or from the input output devices, and out to send data from the processor to the input output devices. This is the first thing that we want to learn. Type. What kind of addressing modes that are permissible for the input output? As you can see here, all input output should be go through through the accumulator, through through the accumulator. Okay, so here the accumulator, which is the AL register, is actually one major or default operand in the input and output instructions. So that means the input and output should always go through the AL register. AL accumulator. Right. So the AL will carry the data. The AL will carry the data either as an in from the port to the microprocessor, or as a out from the AL to the specific input output device. Now we have two ways to indicate the address or the port for the input output. We can specify the port directly. يبقى the addressing modes for the ports is, we have the direct addressing mode. This is the direct, and we have the indirect. Only two addressing modes are permissible for the in-out instructions, or the for the input output instructions, either direct or indirect. Even for the indirect, I don't have the freedom to use any register for the indirect address. I have to put the port number inside the DX register. يبقى الport should be in DX, and the data will be available in the AL register, and vice versa for the in and for the out. The same thing is in the in and the out instructions. Right. Now what else we need? So as an example here, I can actually specify, here is actually an example of an in instruction, okay, using the direct addressing mode. Okay, here I specify the port number, and the accumulator will be my input data will be available in the AL. If I'm using the indirect, that means I have to put the port first into the DX and then perform the in instruction or the out instruction through the AL register. Okay. So now we finished discussing how the input output, or how the in-out interface is being performed for the 8088 and the 8086 microprocessors. Both of them are using what we call the isolated address space for the input output devices. It is also important for us to know that this is not the only way to perform input output for the processors. Other processors use another methodology, which is called what? It's called the memory mapped input output. Okay, يبقى now we learned the isolated input output and for the 8086 machines, and right now we are discussing the second category of the input output interface, which is using memory mapped. The most important thing for me is to characterize and discriminate between the memory mapped and the isolated. The isolated, I have two address spaces, address space for the input output and address space for the memory. For the memory mapped, I don't have that. The input output devices are consuming the addresses of the memory for the input output. So we can specify some range in the memory, okay, that cannot be touched. Okay, this is the memory mapped. So through this range, if ever the microprocessor use or utilize those addresses or the address range from, for instance, as an example, from E0000 till E0FFFF, if this range is reserved for the input output. That means any instruction that will specify a physical address within that range. This instruction is not accessing the main memory, it is actually accessing the input output devices. So the input output devices will take port addresses in that range only. So the processor treats the I/O devices as if it is part of my memory, and if the addresses is specified is within that range, that means the processor will redirect the request for data from or to the processor, okay, will route it through to the input output devices instead of going to the memory. يبقى reading from and writing to the memory map devices uses the same exact instructions as we reading and writing in the memory locations. So right now this is much more flexible. Here I don't need or have in or out instructions. I don't need that, because all the regular move or load instructions that we have used before for the memory would work for me. All what I have to do is to make sure that I am using the correct port for the device that I want to access, and the processor will reroute the transfer of data. Instead of going to the memory, it will go to the I/O. So here is a simple demonstration about. So if this is my address space for the memory, okay, right now I reserve some range of addresses here that will not be utilized by any of the programs, that will not be mapped or utilized for the memory, but they are utilized for the ports, the input output ports. Okay, to cut the long story short, we need to do a comparison between the isolated and the memory mapped. There are 4 regards that we have to know by heart as a comparison between the isolated I/O and the memory mapped I/O. The first thing is the special instructions. Input output isolated I/O needs special instructions اللي هم in and out instructions, while for the memory mapped any data transfer instruction would work. Any instruction will be able to access both the memory and the input output, okay, because here I'm specifying the specific range of addresses for the input output devices. This is the first difference. The second difference is no, which is an advantage here for the isolated I/O over the memory mapped. Here I'm not wasting any of the memory address space for the input output devices, because I have separate address space. Here the blockage of memory are dedicated or reserved. يبقى block of memory is reserved for I/O. Okay, so this is definitely a disadvantage here, okay, compared to the isolated. يبقى هنا because I am losing part of my address space, يبقى definitely this could be identified as an advantage in the isolated I/O compared to the memory mapped I/O. Special instruction, this is a disadvantage for isolated I/O, because here I have much more flexibility. يبقى this is here memory mapped is winning, because here I have much more flexibility to perform input and output operations. I can use any of the addressing modes. All what we have learned about the memory addressing is valid for both the memory and the input output. But here I have a very narrow spectrum for what I can do with the input output devices. Okay, but these are the first two differences. Now the third regard is the speed. Okay, if I am using a particular instruction for the IO, the microprocessor here knows beforehand when he decode the instruction that he is now accessing the input output. So the execution of the instruction will be much faster because the decoding will directly recognize that this is routed directly to the input output devices. However, for the memory mapped, the microprocessor, the memory mapped IO is much slower, because right now the microprocessor will go and check the range of addresses. Okay, is within the range of the IO or it is for the memory. So he have to spend some time to identify whether the instruction will be routed to the input output or routed to the memory. So that's why it is slower. Okay, this is the third difference. The last but not least is the transfer can only occur, okay, between the accumulator and the input output, which is definitely is a disadvantage, as we discussed before. Okay, so here I have a very limited capability of transferring the data, while here a direct transfer from any register to the IO is permissible for the memory mapped IO. Okay, so this is actually conclude the input output and the memory mapped isolated IO, and this is the last thing in the last chapter, in the last theoretical part. Now this is the end of lecture number 28 part 2, and we finish all of the theoretical material of the course, and left for us only a couple of lectures. Through them we will just may solve more programming problems and more problems related to the floating point conversion and floating point arithmetic operations. Thank you, and see you inshallah in the next lectures.